Hello, everyone. Welcome back. Today is going to be dedicated to non-parametric tests. So these are tests that you'll use if we are violating assumptions of a normal distribution, or maybe you have a really unbalanced design, where a standard parametric test is not going to be best suited for actually understanding the data. So basically the biggest difference between a parametric test such as ANOVA or t-test compared to non-parametric like Mann-Whitney U or Kruskal-Wallis is that the parametric looks at the mean. So it uses the mean and standard deviation to make comparisons between groups. With a non-parametric test, we're not actually relying on the mean. We're going to rely on the median, but more specifically ranks. So before we actually get into the worksheet, let's first consider, what a parametric, or sorry, let's first consider what a non-parametric test is doing. A non-parametric test can be really useful because it does not rely on the assumptions of underlying distribution. If you have a really extreme positive or negative skew, or if you have a couple crazy outliers, a non-parametric test is not really going to be influenced by the actual outlier. Now, let's say, for example, you had a distribution that again was really skewed. Say it was a positive skew with an outlier in that right tail. When you have a distribution like this, your mean, median, and mode are going to be heavily influenced, but your mean is going to be the most influenced measure of central tendency. So your mode will really not be influenced by that much. So your mode will still be at that peak. The median might be a little bit to the right of that, but again, not too extreme. But this outlier back here will probably push the mean to be much further to the right compared to the median and the mode. So your mean is not actually really representative of the data itself. And therefore, rather than using the mean and the standard deviation to assess if two groups are different, we'll actually look at the median. That's essentially what a nonparametric test is doing. Because as we can see here, the median is much more representative of the distribution itself. So in this case, a nonparametric test might be better suited to understand group differences. So again, what do nonparametric tests do? They essentially rank the data and perform analyses on those ranks. So we'll go through an example of that in the next slide. And they're useful because they solve distribution problems. Again, if there's an extreme skew or outliers, or if, more importantly, if the data are heteroscedastic. So remember, an assumption of both t-test and ANOVA is that we have equal variability in the dependent variable across all levels of the independent variable. And this, in fact, is really the most important thing to consider when deciding what type of test you should do. If you're violating the assumption of heteros or of homoscedasticity, then your test might not be very robust or not really reliable. For most of the parametric tests that you've learned in this semester, there is an analogous non-parametric test. And we're going to talk about two of them today, or we're going to go through examples of two of them. So, specifically today, we'll do an example of the Mann-Whitney U test, which is used when you would have an independent samples t-test. And we're also going to do an example of the Kruskal-Wallis, which is, again, analogous to a one-way ANOVA. But there are also other types of nonparametric tests. You can do a Wilcoxon rank sum test for a paired samples T. That's really similar to the Mann-Whitney U. The Wilcoxon rank sum test compares two dependent samples, whereas Mann-Whitney U compares two independent samples. The Spearman rank correlation is used in place of a Pearson correlation. This is really useful if you have ordinal data. So rather than numeric data, where Pearson correlation would be best, if you have ordinal data, Spearman rank correlation will be best suited to understand the association between your two variables. We won't be going through a demonstration of those two tests today. But it is important that you know what the associated nonparametric test is, again, for your paired samples T and Pearson correlation. Now, let's go ahead and discuss what a nonparametric test is actually doing. Again, what does this ranking mean? How do we compare ranks rather than compare means? So let's go through a quick example so you can really understand how a nonparametric test both solves unbalanced design as well as outlier issues. So let's say researchers were interested in deciding which show is funnier, The Big Bang Theory, which is going to be in green, or The Office in purple. Three people showed up to the Big Bang Theory focus group, and seven people came to the Office focus group, and I recorded how many times each person laughed. In this study, we have unequal groups because there are only three people in the Big Bang Theory focus group and seven people who watch The Office. So we have an unbalanced design. And we also have really small sample sizes. When you have a small sample size, a mean and standard deviation don't really mean that much in the distribution. If you're just getting the mean of three values, that's definitely not going to tell you about the population. Then, if we take a look at this table, each number represents the number of times one person laughed. So, this person is someone who watched The Big Bang Theory, they laughed one time. This person laughed three times watching The Office, and so forth. And what you can see is that we do have a pretty extreme outlier here. Most people laughed between 1 and 11 times. However, there was one person who laughed 20 times while watching The Office. So, this outlier would influence the mean number of laughters for those who watch The Office. And we want to make sure to take care of that. So, it's not heavily influencing the comparison between The Big Bang Theory and The Office. So now that we've laid out all of these values from smallest to largest, we can assign ranks. So basically, we're going to be assigning rank from 1 to 10 because there are 10 people in total who participated in this study. So it's pretty intuitive. The first person who laughed one time has a rank of 1, and so forth. So the person who laughed three times has a rank of 2. And now, next, we have a bit of a tricky situation. So, two people laughed four times, and we want to make sure they get the same rank. We wouldn't want to give this person who laughed four times a rank of 3, and the next person who laughed four times a rank of 4, because they left the same number of times, so they should have the same rank. And basically, what you're going to be doing here is get the average between what ranks they would receive if they were different. Right, so it would be 1, 2, 3, 4, 5. So these individuals here, their rank will be the average between 3 and 4. Right, so they'll both have a rank of 3.5. Right, and you continue on just the same, this time starting at 5. So we're going to skip 4 here. Right, so this person gets a 5, 6, and again, these two nines here, which means we'll give each of these observations a rank of 7.5, right? Because that's the average between 7 and 8, and so forth all the way till 10. And now you can see that this outlier of 20 is no longer an outlier here because it's just given the rank 1 unit above 9, while the difference between 11 and 20 is 9 units or 9 laughs. The difference in rank between 9 and 10 is simply 1. So now we no longer have the issue of that outlier. If we go ahead and add all of these ranks together, we get a rank sum total of 55. And this will be important when we decide what the expected rank would be for each group. Right? It will be important to know the difference between the actual rank sum and what would be expected if the groups were equal. Right, so let's first determine the actual rank sum. So for the Big Bang Theory, all you have to do is add the rank for each person who watched the Big Bang Theory, right? So we have 1 plus 3.5 plus 5. Gives us a rank sum of 9.5 for everyone who watched the Big Bang Theory. And you'll do the same for everyone who watched The Office. So 2 plus 3.5 plus 6, and so forth. This gives us a rank sum of 45.5. Now, it's not really feasible to compare these two values together because the number of observations are so small, right? So even though they don't look to be the same, they have a different magnitude of rank, that doesn't necessarily mean that there's actually a difference in how people, and how many times people laughed, right? Because there are only three observations for the Big Bang Theory group, which means the rank sum will, of course, be smaller compared to The Office, who had seven observations. So we also should determine what the expected rank sum would be if all groups were equal. So if we had an equal spread across the ranks for the Big Bang Theory and for The Office. So if there was no systematic clustering on either side of the rank, what would the expected rank sum be if these two groups were equal, or if there was no difference in how many times people laughed? Right, so the expected rank sum for the Big Bang Theory is 16.5, and the expected rank sum for The Office would be 38.5. So now we can actually compare the rank sum that we obtained to the expected rank sum if the groups were equal. And what we see here is that the Big Bang Theory, the rank sum is smaller compared to what would be expected, while for The Office, the rank sum is larger compared to what would be expected. So if all groups were equal, we would expect the Big Bang Theory to have a rank sum of 16.5, but in fact, the rank sum is 9.5. And again, the opposite relationship for The Office. The expected rank sum would be 38.5, while for The Office, it's actually 45.5. So we can see that people who watch The Office are laughing more, while people who watch The Big Bang Theory are laughing fewer times. Compare it again to what would be expected if the groups were equal. Now, if you're interested, we can talk about how the expected rank sum is calculated. It's a pretty simple equation. All you have to do is divide the rank sum total by the total number of observations. So in this case, it would be 55 divided by 10. Right? And then you multiply that by the number of observations within each group. Right? So for the Big Bang Theory, it would be times 3. For The Office, it'll be times 7. Oops. So 55 divided by 10 times 7. So that's how we calculate the expected rank sum. Again, if there were no differences in how many times people laughed. Just like I said before, the expected rank, there is quite a bit of a difference between the expected ranks. That's simply a function of the very different sample sizes or the unbalanced design. All right, so now that we have a better understanding of what's going on behind the scenes, how these values are ranked, we can go ahead and move into the worksheet for this week. At this stage, we don't know if it is significantly different between The Office and The Big Bang Theory. So we can actually talk about, what's happening with the Mann-Whitney U test and how to determine if there is a significant difference in the rank. Okay, so back to the worksheet.